Welcome, everyone. Can you hear me? I'm Mike Friedman, representing the Center for Mathematics and Scientific Application at Harvard, and it's my great pleasure to be introducing Yann LeCun, Chief Scientist at Meta. We're running a conference at CMSA on the geometry of machine learning, and this is actually a lecture within that conference, but it's outside the CMSA building because we knew too many people would show up to hear Yann. So we were able to move it to the Science Center where it's appropriate. As soon as we got Yann to agree to give this talk, all the other speakers accepted immediately. So thank you, Yann. It's the easiest conference to organize. Yann is one of these scientists that it would anesthetize the audience if I tried to go through his awards. And also I would need a script. So I'll just mention that he won the Turing Award with Bengio and Hinton a few years ago. I think of him interchangeably with the idea of convolutional neural nets. I'm a geometer as a mathematician, topologist and geometer. And I think that's something we share, a confidence in the geometric imagination. And I know it's something that Yann has always tried to figure out how to weave into artificial intelligence. And it's a vein of exploration that I've greatly admired. I think we're all very much looking forward to this talk, so am I. And without further ado, let me turn the stage over to Yann.
Thank you so much, Mike. Well, I have a terrible confession to make, which is that I'm not a mathematician. I'm not really a computer scientist either. I never actually studied computer science. So I'm not exactly sure what I am, but I'm going to talk about machine learning. I was told this was a bit of a more general audience than the one at the workshop, so I made this a bit more of a wide audience talk than, still technical, but not very. A little lightweight on the theories, that's for sure. And I want to talk about the future of AI and how can we make significant progress towards more intelligent machines beyond what they are capable of doing. And I tell you right now, there is a lot of work to do. We're nowhere near matching human intelligence or even animal intelligence with the type of techniques that we have access to at the moment. So one big question we can ask ourselves is, do we actually need AI systems with human level intelligence? And the answer is probably yes, because there's the future in which each of us walks around with AI assistants kind of helping us in our daily lives at all times, perhaps living in wearable devices like smart glasses like the ones I'm wearing at the moment. Actually, you guys need to smile. Okay, you're in the box. And those things will be sort of helping us at all times. And it's like we'll be their boss. So it's kind of like we'd be kind of running around with a team of virtual people kind of helping us at all times. And of course, for this, we need AI systems that have intelligence that is in some way similar to human, because that's the kind of entities that we are the most familiar with interacting with. But the technology is nowhere near where it needs to be at the moment for that. So the main issue is that current AI architectures and machine learning techniques suck compared to what we can observe in humans and animals. The type of efficiency in learning that we see in animals and humans is just astonishing, and we're not matching this, at least at the moment in many instances. So early on in machine learning, the main technique was supervised learning, and then there was a big fashion around reinforcement learning for a while. Now it's used a lot, of course, to fine-tune large language models, but in themselves, those two techniques are really insufficient. The type of learning that we observe in humans and animals is very different. It's neither supervised nor reinforced, for that matter. It's more like self-supervised learning, or something that has really revolutionized AI and machine learning over the last few years, which, at the principle, the underlying principle are very similar to supervised learning, but there is no clear difference between input and output. I'll come back to this. This works astonishingly well for training a system to understand the structure of sequences of discrete symbols, such as language, code, mathematics to some extent. But the problem is that it only works for sequences of discrete symbols. It doesn't really work for kind of natural signals, self-supervised learning. It starts to work, but the techniques are very different, and that will be the main topic, really, of this talk. There's other limitations with current AI architectures, which is that the type of inference that they perform is basically feed-forward propagation through a fixed number of layers of some neural net. And that's computationally limited. There's a lot of functions you cannot represent efficiently by just stacking a fixed number of layers of alternating linear operators and nonlinear pointwise operators. And the idea of training a system to predict the next item in a sequence works for discrete symbol sequences, but not really for anything else. The other issue also with current architectures is that they use autoregressive prediction. So they use their own predictions as input to make further predictions. And that leads to divergence, or hallucination, as people call it. So there's a lot of things that really we're missing to kind of match the type of intelligence we observe in humans and animals. Humans and animals have mental models of the world. The behavior is driven by objectives, by tasks, goals, if you want. They can reason and they can plan complex action sequences, all things that chatbots and LLMs are essentially incapable of, or at least not to the level that we'd like. So we need systems that understand the physical world, systems that have persistent memory, systems that can plan complex actions so as to fulfill an objective or accomplish a task, systems that can reason. In particular, they can spend more time solving difficult problems than simple problems, and systems that are controllable and safe. Okay, so let's start with this idea of world model. We have mental models of reality that allow us to predict what's going to happen, particularly what's going to happen as a consequence of our actions. And this is really what allows us to plan. And the type of learning that is taking place in humans and animals in the first few months of life is a little mysterious. So this chart was put together by my colleague and friend Emmanuel Dupoux, who is a cognitive scientist in Paris. And it indicates at what age infants learn basic concepts about the world, like object permanence, the fact that some objects are stable when you put them on the table, they're not going to fall. That objects belong to different categories. Babies that are 5 or 6 months, they don't speak, don't manipulate language, but they certainly know what the difference is between a table and a chair and a cat and a dog, without knowing the names of it. And it takes about 9 months for infants to learn basic notions of intuitive physics, like gravity, inertia, conservation of momentum, this kind of stuff. So if you show a 6-month-old the scenario at the bottom left, where a little cart is on a platform and you push it off the platform, it appears to float in the air. 6-month-old won't pay attention much. A 10-month-old will be extremely surprised, perhaps look like a little girl here, because by then infants have learned that objects that are not supported are supposed to fall. So how do we get machines to learn like babies? And we've not solved that problem. And the reason you can tell that we've not solved that problem is that we don't have domestic robots. We don't have self-driving cars that are completely autonomous, level 5. We have them, but we cheat. But we have systems that can pass the bar exam, they can solve math problems, do all kinds of stuff that are intellectually challenging for most of us. But we still don't have robots that can do what a cat can do, or can do that what a 10-year-old can do the first time the 10-year-old tries. You tell a 10-year-old for the first time, clear out the dinner table, fill up the dishwasher. 10-year-old can do it without being trained to do it, basically the first time. 17-year-old can learn to drive a car in an astonishingly short time, maybe 10 or 20 hours of practice, without causing accidents mostly. And we have millions of hours of training data. We still don't have self-driving cars, except with cars with lots of extra sensors like LiDARs and complete mapping on the environment and all kinds of tricks. So obviously we're missing something big. And this is another example of what's been known as the Moravec paradox, which is that a lot of things that we consider intellectually challenging for humans, playing chess, solving integrals, stuff like that, turned out to be algorithmically relatively simple. And the same is true for producing nice-sounding text or answering a question as long as you've been trained to produce the correct answer. Yet, we don't have robots that are nearly as dexterous as any primate or even a cat. So this may be explained by the following very simple estimate. So a typical large language model is trained with something like 30 trillion tokens. This is the number I got for Llama 3, I think. A token is like a subword unit, so that's something like 2 × 10⁻13 words. Each token is 3 bytes, so the total amount of data used to train a typical LLM is about 10⁻14 bytes. It would take any of us 400,000 years, maybe 500,000 years to read through that. It's just an enormous amount of text. Now compare this to what a human child has seen, a 4-year-old has seen during his or her life. 4 years of life is about 16,000 hours for a young child, which, by the way, is a small amount of video. It's about 30 minutes of YouTube uploads. And information getting to the visual cortex through the optic nerve is about 1 byte per second times 2 million. We have 2 million optic nerve fibers, each of which carries about 1 byte per second. So during wake hours, it's about 2 megabytes per second. Multiply this by 16,000 hours, and it's about 10⁻14 bytes. Okay, so a 4-year-old has seen as much data as the biggest LLMs trained on all the publicly available text on the internet. Now, you might say that the visual data is much more redundant than the text on the internet, which is true. But in fact, that's exactly what you want. To train a system to understand, to capture structure and dependency in training data using self-supervised learning, you need redundancy. If you don't have redundancy, you can't learn anything. You can't learn anything from completely random bit strings. So it tells you a number of things. The first thing it tells you is that we're never going to get to human-level AI by just training on text. It's not going to happen. Despite what you might hear for some of the more optimistic sounding CEOs of various AI companies in Silicon Valley, it's just not going to happen. It also means that we need to make some serious progress if we want to have robots that can be useful. There is countless companies that are being formed that are building humanoid robots, and you see all those videos of those robots doing impressive things. But in fact, the secret of all that is that none of those companies has any idea how to make those robots smart enough to be useful, except in very narrow tasks for which they have to be carefully trained. So that's an issue. So that gives an opportunity for researchers and scientists trying to kind of make progress in AI. There's still a lot of work to do. And it may not require hundreds of billions of investment in GPUs. Okay, there's a second issue, which is inference. So I mentioned the limitations of inference by forward propagation through a fixed number of operations. A lot of things that we're doing require much more sophisticated computation than this. And in fact, I would submit that a more powerful way to perform inference is through optimization. So instead of a system computing its output by, this works, by just propagating through a fixed number of layers in some sort of neural net and then producing an output, the design I think is that's much more preferable would be a system that extract information from its input, produces a representation of the input if you want, but then has another big neural net or learning machine with a single scalar output, let's call it an energy, that would measure the degree of compatibility or incompatibility between the input and a proposed output. Okay, so propose an output, and then this function, which may be a very big neural net, compares, tell you to what extent this output is compatible with this input. Okay, I put an image of an elephant here, and then I put the label elephant, and I want the output of the scalar output of this function to be, let's say, 0. If I put another label, table, chair, cat, whatever, I want the output to be larger than 0. Okay, so a measure of incompatibility, if you want, between input and output. So the way you perform inference with a system like this is through search. You basically put an input, and then you search for an output that minimizes the scalar output. The output is not represented, it's implicit in those kind of square boxes. You search for an output that minimizes the energy function. And really, this type of inference by optimization is very classical in AI or probabilistic inference or this kind of stuff, right? There is a lot of really classic, a lot of classic work in path planning, all kinds of planning actually. Shortest path between cities, shortest circuit between cities, SAT. Finding values of Boolean variables that satisfy a Boolean formula, logical inference. All of those things can be reduced to optimization problems, but not necessarily to forward propagation to a fixed number of layers. So this kind of inference by optimization allows for what some people call zero-shot learning, which means producing answers or solution to problems without being trained to produce solutions to that problem. Basically just coming up with a new solution to a problem. Okay, this is what search and optimization can do. This is also perhaps a good model for the type of inference that takes place in humans that psychology calls system 2. So system 1 is decisions you're making or actions you're taking instinctively, basically without really having to think about it too much. And system 2 is the type of actions that or decisions you make deliberately by kind of thinking about it and maybe using your mental model of the world to sort of predict the outcome of particular actions you might take. Now, this is not what LLMs are doing. LLMs take a window of a sequence of symbols, then run that through some big neural net and produce a guess as to what the next symbol is. And then once you have produced the next symbol, you shift it into the input, and then you produce a second symbol, shift that into the input, third symbol, etc. That's called autoregressive prediction. And it's very classical. It's been around with us for 7 decades or something, if not more. Nothing new about that. But there is kind of a basic limitation with this type of thing, which is that there's a fixed amount of computation devoted to producing any single token. So the only way you can entice a system of this type to spend more resources, more time on complicated question is to trick it into producing more tokens. This is a trick called chain of thoughts, right? You tell the system, tell me all the steps of your reasoning, which may not be reasoning actually. And as a consequence, the system will just spend more computation. It's going to produce more tokens, so it's going to spend more computation. But it's kind of a hack. There's another issue, which is perhaps even more dire, which is that autoregressive generation is kind of a divergent process. You can never exactly predict what token or what word follows a particular text. what those systems are trying to produce is basically a probability distribution over all possible tokens, of which there is typically about 100,000 possible tokens, right? So it's a big vector of numbers between 0 and 1 that sum to 1. And you might, always pick the token with the highest probability and just generate a sequence this way, or you might, sample from this distribution. Whatever you do, might be some probability that at any point, the token that's generated takes you outside of the set of sequences of tokens that would be correct answers, right? So the set of all possible sequences of tokens is a tree, okay, represented by this blue disk, essentially, where each leaf is kind of the terminal symbol in the tree. They don't have all the same length, but it's a tree. Within this tree, there is a subtree, which corresponds to all the correct answers corresponding to a particular prompt. There may be some probability so that at every token you produce, the token takes you outside of the correct subtree. Because it's a tree, there's no way to come back, right? You're out, you're out. So if you make the hypothesis, which of course is most likely wrong, that this probability is the same for regardless of where you are in the sequence, and the errors are independent, then the probability that a sequence of n symbols would be correct decreases exponentially, like 1 minus the error rate to the power n, where n is the number of tokens. Okay, this is one way LLMs hallucinate. So this is not really fixable without some major redesign of how those systems produce their answers. We don't produce answers by just blurting one word after another. We think about the answer we're going to produce. We have an abstract thought that represents this answer, and then we turn it into text, okay? But that's kind of a second step, if you want. There is an advantage, though, to LLMs, which is that they are very easy to train, and the training scales very well. So this is a representation of GPT-style architecture, where basically, secretly, a large language model is actually trained to reproduce its input on its output. You give it a sequence of symbols, and you train it to just reproduce the sequence of symbols on its output. But it cannot just learn the identity function, because the connection is designed in such a way that to produce one particular symbol, this one, for example, this green one, it cannot look at the corresponding symbol on the input. It has to only compute it or predict it from the symbols to the left of it. So implicitly, it's trained to produce the next symbol in the sequence, but it does this in parallel over very long sequences, and you can do this very efficiently. So those GPT architectures scale. This is why people are using them instead of alternatives at the moment. But it's very limited. Okay, what we really want is perhaps emulate this ability that humans and animals have to have a mental model of the world, a world model. Okay, what is a world model? World model is given a representation of the current state of the world, which you might have estimated by observing past, observing the world and then, representing its state. Let's call it SX. And given an action that you imagine taking, can you predict a representation of the next state of the world that will result from taking this action? And the way you can train a world model is very simple. You give it a bunch of observations, and then you run through the encoder, the predictor. You give it an action that you know is taking place there, and then you feed it the next state of the world. Basically, I mean, it's not a state; it's an observation. You run it through the same encoder as you run the previous state. That produces a representation for the new state of the world, and then you minimize the prediction error, the difference between the representation of the current of the next state of the world, given the prediction obtained from the previous state of the world, obtained from perception. So one idea, which is very natural, which a lot of people have been working on, including me for many years, is to use the same idea as LLMs, which is to train a generative model to predict what's going to happen next in a video, right? So take a video, say a full video, corrupt it by masking the second half of it, let's say, okay? And so this encoder sees only the first half of the video. It produces a representation of it and then runs this through some sort of decoder, predictor decoder, that given the action that you know is taking place in the video, produces the rest of the video at the pixel level, okay? So it just predicts all the details, everything that is supposed to take place in the video. And that's essentially an impossible task. It's an impossible task because there are many things that can plausibly happen in a video that may happen in a non-deterministic way that you cannot predict. And so if you train a neural net to make a single prediction for what's going to happen next, the best thing you can do is predict some sort of average or aggregate of all the possible futures, right? And in fact, that's exactly what happens. So this is from an old paper almost 10 years ago now. We trained some big neural net for the time with 4 frames and then train it to predict the next 2 frames. And the predictions are really blurry. You see the same thing here. So those are kind of little like symbolized videos of cars being looked at from the top on a highway. The central car here is fixed. And this is a neural net trained to predict what the cars around it are going to do. And you get those blurry predictions because it doesn't know if the car is going to accelerate or brake. And so it predicts the average. Now, using various techniques with latent variables, you can feed your neural net with latent variables that you either sample from a distribution or you optimize in some way. And you can correct this flaw to some extent. And at least for simple videos like those highways produce videos that are crisp. And depending on the value of the latent variable, would predict multiple different futures, right? So with a latent variable, you can sort of parameterize all the potential plausible futures that will happen in the video. Unfortunately, it doesn't really work for natural videos. If I take a video of this room and I point it on this side and I kind of rotate slowly, and I stop here and I ask the system predict the rest of the video, it will predict we are in a room and the chairs are red and there's probably a wall on the side. There's no way it can predict the texture of the floor, the texture of the wall, and it cannot possibly predict what all of you look like and where you sit, right? I mean, that information is just not predictable. So either a system like that has to kind of make up some plausible instantiation of what may happen, or predict an aggregate of everything that happens. But basically, the problem of predicting at the pixel level what goes on in a natural signals, particularly video, is basically impossible. So you say, okay, well, we can do like LLMs. LLMs don't actually predict a single token. They predict a distribution over tokens. Okay, so what that means is that we need to parameterize a distribution over a high-dimensional continuous space, like the space of all possible video frames. And that's just mathematically intractable. The best way we can represent distributions is by, we can do it the same way physicists do it. You write down an energy function, and then you do e to the minus this energy function and normalize. Most of the time, that normalization term, which is a big integral, is intractable, at least for interesting distributions. So here's a proposal. The proposal is just don't predict at the pixel level. Predict at the representation level. Okay, so we're going to build this architecture, which I call JEPA. That means Joint Embedding Predictive Architecture. And basically, instead of predicting all the pixels, we're going to predict a representation of the pixels. Okay, so we're going to run the video through an encoder and this partially matched video through an encoder, maybe the same encoder. And simultaneously with the encoder, train a predictor to minimize this prediction error. But the prediction is going to take place in representation space. In the representation space, it's an abstract representation. It may not contain all the details about the world that are just not predictable. We might eliminate all the details that are not predictable, making the prediction task much simpler. So that's the comparison between those two architectures. This is generative architectures, predict all the details of the variables you want to predict. And this is the joint embedding predictive architecture. Find a representation within which you can make predictions. And that representation will not contain all the details. Now, if you think about this, this is how we apprehend the world. We find representations that allow us to make predictions. We don't represent the world in all of its details. The entire purpose of science even is to find those representations so we can make predictions. Representations that ignore the details. So in fact, if I want to predict the trajectory of planets viewed from the Earth, right? They seem kind of complicated because sometimes they go forward, sometimes they go back, etc. Right? And there's some periodicity, and people in antiquity kind of figured out how to predict this. But it was kind of complicated until the appropriate representation for the problem was figured out, which is that the Earth rotates around the sun, or the other planets rotate around the sun, and they have elliptical orbits, and then it all becomes simpler, and you can predict everything. And to predict the trajectory of any planet like Jupiter, where is Jupiter going to be 100 years from now? You don't need to know all the details about Jupiter. As a matter of fact, you only need to know 6 numbers, 3 positions and 3 velocities, and that's it. So the question of finding appropriate abstract representations that eliminate all the details in such a way that they allow us to make predictions is really fundamental to science and to intelligence in general, I would argue. In fact, to expand a little bit on this dimension, in principle, I could describe everything that is taking place in this room at the moment in terms of quantum field theory. I would have to measure the wave function of all the quantum field in this room, which of course is an impossible task. And then I would have to have some super gigantic, powerful quantum computer that would allow me to kind of make the prediction, assuming there is not too much interaction with the rest of the universe, which of course is not the case. So it would be an impossible task. So what do? We invent abstractions. Okay, we have particles, we have atoms on top of that, molecules. On top of this, in the living world, we have proteins, organelles, cells, organisms, individuals, societies, ecosystems, right? So we have this whole hierarchy of representations, and at each level allows us to make kind of bigger, bolder, longer-term predictions while eliminating a lot of details about the level below. In physics, there is actually kind of 2 systematic ways of doing this. One of them is called renormalization. Renormalization, or with renormalization group theory, is a way of basically representing the state of a group of sites or particles or spins or whatever you want in sort of abstract way, if you want, so as to kind of not have to deal with like the details of the actual state. Similarly, in physics, there's the notion of entropy, right? I can make predictions about the property of a box full of gas, PV equals nRT, right? If I compress the gas, the temperature is going to go up, things like that. But I've ignored the position and velocities of each of the individual molecules in that gas. And we call this entropy, right? We even have a name for the information we leave behind when we go one level up in the hierarchy. What's interesting about this hierarchy is that every level in the hierarchy is a different field of science. So perhaps a field of science is actually defined, or natural science at least, is defined by the abstraction level that we choose to make predictions. Okay, so much for philosophy. So if we're able to train a system to have a mental world model of the world, right, allows it to predict what's going to happen, perhaps as a consequence of its action, how can we use this as the basis of an intelligent system? So I wrote this sort of vision paper 3 years ago that I put online for comments about where I think AI research will go over the next 10 years. This was before the LLM craze, but I haven't changed my mind about this. And here is an example of how this could be implemented. So this is an intelligent AI agent. It's observing the world through a perception system that gives it an idea of the current state of the world that it can currently perceive. Of course, there is a lot that the agent probably knows about the world that is not currently perceivable. Like, we know the state of our house to some extent and things like this. Like we have, a complete idea of the state of the world. So, which is stored in our memory. We don't currently perceive it. So we might want to combine what we perceive about the world with the content of a memory, feed this to our world model, and the world model is going to take an imagined sequence of actions that we imagine taking, and is going to predict the resulting state of the world or sequence of states that the world is going to go through as a consequence of the actions that we imagine taking. Now, what we can do is feed this predicted state to a task objective that measures to what extent, so that's an energy function, that measures to what extent a particular task has been accomplished, a goal has been reached. So this guy will produce a scalar output 0 if the task has been accomplished, and a positive larger number if it's not, and potentially indicate some distance to the objective. And we might have other cost functions, other objectives that are guardrails, which would prevent the system from sort of taking actions that would not be safe, right? So if I have a domestic robot and I ask it to get me coffee, it goes to the coffee machine and there is someone standing in front of the coffee machine. I don't want the robot to just slash that person to pieces to get access to the coffee machine. So obviously we'd need to kind of hardwire some guardrail objectives into that robot. And that robot would not be able to escape those guardrails because the way it operates, the way it produces an output is that it searches for an action sequence which, according to its internal world model, would actually satisfy those objectives, the task objective and the guardrails. And it can't escape that. This is by construction, okay? So if we put a guardrail in it, it has no choice but to satisfy it. And so this is an example of this inference by optimization I was telling you about before. Really, what it is planning is an example of classical planning as it is used in robotics. Now, if we have a world model that can make predictions to a certain horizon, we can probably apply it multiple times in an autoregressive fashion and feed it with a sequence of actions every time. And so perhaps this world model is just a mechanical model of a robot arm or something. And so it's very simple thing. And it's a differential equation, for example, that we can apply multiple times. And in fact, this is a classical way in optimal control of planning a sequence of actions. You have a model of the system you're controlling, generally a set of handwritten equations, but in our case, we're going to learn it. And then a cost function that characterizes whether a task has been accomplished. And then you plan by optimization a sequence of controls or actions that will minimize this cost, subject to maybe some constraints. Completely classical in optimal control is called MPC, model predictive control. But what's complicated about this here is that this world model may be really complicated, maybe some big neural net that is trained from lots of data. The input may be video, the actions may be complicated. There may be some discrete and non-continuous behavior in the function, the cost function in the space of those actions may be extremely irregular, it may be non-continuous, maybe even if all those modules are mostly differentiable, they could be kind of non-continuous things. So for example, if I want to go from where I am standing now to the other side of the desk here, I can choose to go to this side and that side. And that's a discrete choice, which will result in two completely different costs for my going to the other side. Okay, it's going to be more costly if I go this side than if I go from that side. Yet the difference in action that I can take to choose between those two is very small. I can change my initial action from taking a step in this direction to taking a step in that direction. That could be a very small change, yet it's going to result in a discontinuous change in cost. So those functions are going to be very complicated. This is going to pose, since we're supposed to talk about geometry, this is going to pose some major issues in optimization here that are not really solved, that a lot of optimization people have been thinking of for many decades, actually, in the context of optimal control. But here, it's even more complicated given the fact that those world models might end up being very large neural nets. The world is not entirely predictable, so the way you handle non-determinism is through latent variables. Neural nets are deterministic functions, but you can feed them with latent variables that are sampled from a distribution or maybe inferred in another way, which basically parameterize the set of plausible predictions. And then the planning problem becomes even more complicated now because you don't know the value of those latents and you have to plan in the context of uncertainty, essentially. Ultimately, what we want to do is build a model like this. And I should tell you right now, nobody has done this, okay? But build a model that is hierarchical in the way that I was describing earlier, in such a way that we can use it to do hierarchical planning. What does that mean? If I'm sitting in my office at NYU and I decide I want to be in Paris tomorrow, I cannot possibly plan my entire trajectory from New York to Paris in terms of elementary actions I can take, which in the case of humans are millisecond by millisecond muscle controls. I have to plan at a much higher level, right? Which would be, okay, I mean, New York, the best way to go to Paris is to go to the airport and catch a plane. That requires a mental world model of, what does it mean to go to the airport and to catch a plane, and what a plane can do and things like that. But it's a very abstract model at a very abstract level where the actions are very high level. Things like, taking a taxi or something to go to the airport, or things like, getting an airplane ticket or something like that, and jumping on a plane. But I have a sub goal now, which is getting to the airport. And maybe my sub goal, my cost function, my new cost function is not my distance to Paris anymore, but it's my distance to the airport. Okay, so now it's a shorter objective. I want to go to the airport. I'm in New York, so I can just go down on the street and hail a taxi. Now my sub goal is going down on the street. How do I go down the street? I'm sitting in my office. I need to go to the elevator, push the button, get into the elevator, walk out the building. How do I go to the elevator? I need to stand up from my chair, pick up my bag, open the door, shut my door, avoid all the obstacles, say bye-bye to my students, blah, blah, blah. There's a point in this hierarchy where I have all the information I need, and I may not actually need to plan formally. I can just take the action because I'm kind of used to doing it. So I can revert to system one, which is sort of reactive actions. Okay, so this hierarchical planning requires hierarchical world models that work at different timescales and different levels of abstraction. This is kind of a level of abstraction of going to the streets and catching a taxi, and this is a high level of abstraction of going to the airport and catching a plane. How do we train a system like this to learn the appropriate level of abstractions? And then once we have it, how do we use it to plan hierarchically the way I just described? This is completely unsolved. If you are, I don't know, studying a PhD in AI, this is a good problem to start thinking of because it's completely unsolved. It's wide open. So put this whole thing together and you arrive at what some have called cognitive architectures, which is kind of a way to put all of those modules together. Perception, memory, which is kind of like the hippocampus in the mammalian brain, the world model, which is probably in the prefrontal cortex in humans, all kinds of cost functions, some of which are really intrinsic costs that were kind of hardwired into us by evolution, but many of them are costs that we define ourselves, basically sub-goals and things like this. And then a way to sort of search for action sequences, which, according to a world model, we produce the outcome we want. Okay, so we have kind of an overall architecture for the AI system. How are we going to train those world models from observation using self-supervised learning? So the idea of those joint embedding architecture goes back a long time, the early 90s, in fact. It was a type of model we used to call Siamese networks, and they've kind of evolved over the last few years to some extent. And basically, we have this sort of architecture with two encoders, which may or may not be the same, a predictor, which may be conditioned by an action, which may depend on latent variables to account for the non-determinism of the world, and then some prediction error cost function, and maybe some other cost functions that drive the system to learn appropriate representations. Okay, the way to conceptualize the way we want to train a system of this type is really what a system of this type kind of basically produces a scalar output, which, as I said before, it can be interpreted as an energy that measures the incompatibility between the input and the output, between X and Y. And what we need is a way to train our system in such a way that it produces low energy for training samples that we observe, pairs of X and Y that we observe, and higher energies for pairs that we do not observe. And that's where it becomes complicated. So let's imagine that we have two scalar variables here, X and Y, and we have training samples that are those black dots. And what I want is my learning machine to learn an energy function that takes high values, that takes low value on the, near the training samples, and higher values outside. So basically, some sort of landscape. It could be high dimensional because that depends on the, on the dimension of X and Y, or at least the representations of X and Y. So how do I do this? How do I train a parameterized function that produces a scalar output to give me low output for things I train it on, but higher output for things I don't train it on? There's two methods. And basically, a big issue there is to prevent collapse. So if I just train a system like this to just minimize the prediction error, I just show it pairs of X and Y, I just minimize the prediction error, it will collapse. Basically, it will ignore X and Y, and it will produce Sx and Xy that are constant. And then the prediction problem becomes trivial. And so the prediction error is 0. It's going to be 0 for everything. Okay? Not a good way to capture the dependency between X and Y. So I need to have a way of making sure that their energy is large for things that the system is not trained on. And the advantage of representing a dependency between variables as an implicit function of this type is that I can represent dependencies between X and Y that are not functions. Okay? There's no function that maps X to Y here because there can be multiple Ys for a given X. And so using an energy function is basically an implicit function that represents dependency between the two. Okay, so this energy function can collapse. If I merely train it to minimize the energy of those training samples, which are those blue beads, let's say this is X and this is Y, I might end up with an energy surface that is completely flat. So the way to prevent this from happening is there's two methods that I know about. One is contrastive method. So you generate those green points, which are outside the manifold of data, if you want, and you push their energy up. So change the parameters of your neural net so that the energy goes up. Is high for those green dots. And the big question is how you generate those green dots. And then there's another big question, which is that if the dimension of the space within which you do this is high and the learning machine is fairly flexible, then the number of those contrastive points you're going to have to generate is going to grow exponentially with the dimension. And that's not a good idea. It doesn't scale very well. I used to be a big fan of those methods, contributed to inventing them, but I became very pessimistic about them. What I prefer is regularized methods. So those are methods that basically have a term, regularizing term, that tries to minimize the volume of space that can take low energy. So that when you push down the energy of certain parts of the space, the training samples, the rest has to go up because there is only a limited amount of low energy volume to go around. So those are the two methods. the two categories of methods. And I became kind of more of a fan of the second category. I'll come to this in a second. So you can sometimes turn energy-based models into probabilistic models by using a Gibbs distribution, take exponential minus the energy and normalize, and you get a properly normalized conditional distribution of y given x. The problem is that most of the time, for any reasonable f, the bottom is intractable. And so you don't need to deal with this. Just deal with the energy function directly. I made a list of various methods that people have proposed over the decades as to they can be interpreted in this framework in terms of whether they're contrastive or regularized. I'm not going to go through the list, but it's interesting to go through that exercise. So how are we going to use this self-supervised learning, perhaps, let's say contrastive to start with, to train a system, for example, to represent images so that we can do image recognition, for example. So the process is that we're going to train this joint embedding architecture in some way. And then once it's trained, we chop off the predictor. We just use the encoder to produce a representation. And then we train a very simple classifier on top of it using supervised learning to do, for example, image recognition or depth estimation or something like this. Contrastive methods are very simple. They consist in showing pairs of images that are basically different versions of the same content using distortion or corruption of some kind, and then training the system to produce a representation of the original image from the distorted or corrupted one. And then you have to have contrastive samples, which are pairs of images that you know are different, and then you push the predicted representation and the actual representation away from each other. Okay, so you have some loss function that is going to pull those two guys together, and is going to push those two guys away. And this kind of works, but it never produces representations that fill spaces that are more than about 200 dimensions when you train them on things like ImageNet. There's another type of method called distillation, and those have been considerably more successful. Those are sort of like regularized methods, also, although the main issue is that we don't really understand why they work, although there is some theoretical work. So basically, you take an input, you transform or corrupt it, you get a different version of it. You run this through an encoder, produce a representation, run this through an encoder with the same architecture but slightly different weights, then run through a predictor and then minimize its prediction error. But you don't backpropagate gradient through this encoder because you're not going to train the weights of this encoder through gradient descent. The weight of this encoder are going to be essentially the weights of that encoder, except you're going to accept those weights. This weight vector is going to be a running average of the weight vectors of that encoder over time. Okay, take the past several values of the weight vector and average them. And that gives you the weights of this encoder. Basically, the weights of this encoder cannot move as quickly as the weights of that encoder. This guy gets gradient backpropagated and updates its weight, and then it basically updates the weight of this guy, which kind of is a low-pass filtered version of the previous weights. Somehow this works. Somehow this doesn't collapse. Why? I don't know. It's kind of mysterious. The idea came from intuitions, from reinforcement learning for some reason, but there is a bunch of methods. This one came from DeepMind. Those 4 came from my colleagues at FAIR, and there is some theoretical work also from some of my colleagues at FAIR and at Stanford that attempt to explain why this does not collapse every time. And if you make the hypothesis that the encoder and the predictor are linear, then you can show that there are fixed points of the gradient descent dynamics that are not collapsed. But that's the best explanation we have for why this works. But it's not entirely satisfactory. Also, it's very weird because there is no function that you can monitor that goes down as you train, because you're not actually minimizing anything, even though you're doing gradient descent. It's very strange, but it works really well. And so there's a technique, a particular instance of this technique called DINO. It's made by French people at Fair Paris, so they pronounce it DINO. On this side of the pond, they say DINO. But and it works really well. It produces really good results when you train it on distorted versions of ImageNet and whatever. And when you scale it up, you have a very large network, a lot of training data. This paper is a few months old. You can show that the performance of those self-supervised learning systems surpasses or at least matches the performance of purely supervised systems with considerably less data. Okay, so this is the first time, it's only a few months old, where it's very clear that for image understanding, self-supervised learning now surpasses the best supervised learning methods. So if you have money to spend, you're better off kind of spending it on scientists to kind of fine-tune self-supervised learning methods and collect unsupervised, unlabeled data, rather than spending it on people to label your data. And it wasn't clear until March or April. This DINO model is really kind of amazing. It can produce generic representations of images that can be used for all kinds of applications, not just image like object recognition, but all kinds of stuff in medical imaging, in biological image analysis, in astrophysics, in all kinds of domain, remote sensing, all kinds of stuff. And basically is produce state-of-the-art performance when you train a head on top of the representation for a wide variety of visual tasks that are either very kind of semantic or low level. Okay, but can we use those representations to train a world model so that we can do planning, as I was explaining earlier? And the answer is yes. So this is work by led by Leral Pinto, who is a colleague of mine at NYU, a roboticist, and myself with two of our students, Kathy Zhu and Henkai Pan. And what we did here is take the DINO encoder, so feed images to the DINO encoder, and then train a predictor on top of it, which is action conditioned, so that you have a view of the world and an action that the robot is taking. Can you predict a representation, the DINO representation of the next view of the world that results from taking this action? And then can you use it for planning a trajectory so as to arrive at a goal and fulfill the task? And the answer is you can do this in certain cases. And the performance is better than sort of previous systems that people have worked on. Dreamer v3 is a system from DeepMind. And this is model predictive control, essentially. So start with an initial state, run this through the DINO encoder, then run your world model with a hypothesized sequence of actions, measure the distance with an encoded target image, and then through optimization, figure out a sequence of actions that will minimize this distance, and then take the first few actions in the actual environment, and then perhaps replan. And this works really well. Let me skip ahead a little bit and show you a demo of that system for a particular task here. So the predictor has been trained sort of relatively generically, but these are target things. This is the initial state, and these are the actions that are planned by the system so as to move those blue chips as close as possible to those configurations as possible in something like 25 actions. Okay, it's limited to 25 actions. And this works pretty well. The dynamics of the environment here is pretty complicated because those blue chips kind of interact with each other and everything. And the same technique kind of works pretty well for a wide variety of different environments. Let's see. Okay, we're going to have to watch this video again because it doesn't want to switch to the next slide. So this is far from perfect in various respects, but it's kind of a good example of kind of learning a task zero shot. You don't need to train the system to accomplish a task. It has a good world model. It will accomplish the task by planning. No need for training, for reinforcement learning, for anything, for learning a policy or anything. Planning purely. a similar project led by Amir Bar, who was until recently a postdoc with me at FAIR, who is now a research scientist at FAIR. And there's some demos you can look at here. And this is for navigation. So he took videos from mobile robots where you get a view from the robot, and then the robot moves, it translates and rotates, and you know the transformation because you have odometry from the wheels. You get a different view. Can you predict the next view of the world at the representation level from the previous view and the displacement, the transformation matrix, basically? And if you can do that, can you use it to plan? So, can you tell a robot here, like, go to the blue trash can? It actually it's very far in the back, but it sees the blue trash can, and it can sort of plan a sequence of actions to go to the blue trash can. And this works pretty well. This paper actually won the Best Paper Award, honorable mention at the last CVPR conference. It's pretty cool. I mean, I think there is a lot of situations now that we're going to be able to handle with those world models with slightly more generic ways of training them, perhaps like the ones I'm going to tell you about just now. So this is work, this is iJEPA, V-JEPA, and V-JEPA 2, Video JEPA 2, which is more recent, where it's, again, one of those distillation type model where you have two encoders and they share the weight with this exponential moving average trick. And you train the system to predict a representation of a full image from a representation of a partially masked image using an encoder. And what we show with this experiment is that this system, which is not trained by reconstruction, purely joint embedding, works, trains really quickly and produces really good performance, much better than an alternative project done by our colleagues at FAIR. This is MAE, masked autoencoder, and this one is trained by reconstruction to predict pixels, right? So you take an image, you corrupt it by removing some patches, and you train a gigantic system to reconstruct the full image. This basically was not a big success. The representations you learn from this are not that great, and it takes a long time also. More recently, there's a version of this that works on video. So you take a video, you corrupt it by masking a whole bunch of areas within the video from the full video, and then you train again a system to predict the representation of a full video from the representation of the partially masked one through a predictor. Perhaps the variable that is fed here is the location of the places that are masked. And what they get at the end is that you get a good representation of videos that you can use for classifying actions, for things like that, and et cetera. But what's interesting about this is that it can learn some level of common sense, where it's able to do, if you show it a video where something impossible occurs, like this ball is thrown in the air and just all of a sudden disappears, you apply this video JEPA system with the sliding window over this video, the prediction error will shoot to the roof when this occurs because it knows it's impossible. And so that's interesting because that's kind of the first models that we have that have learned a little bit of common sense, if you want, or intuitive physics, completely unsupervised. So we have a long paper that describes a whole bunch of experiments about this, which I don't have time to go through. And a new version of this called V-JEPA version 2, more recent, where you can see some examples there. And there is two phases, one where we just train on video, the other one where we train a predictor, which is action conditioned, that we can use to plan action sequences for robots. And let me show you a short video of that. So this is an unfamiliar environment. The system has not been trained on. And it doesn't know a priori, like there's no calibration of the camera or whatever, and it's pretty robust to the particular anatomy of the robot and the position of the camera, and it basically plans a sequence of actions so as to reach a particular goal, which in this case is moving this cup, down on the table. So let me skip ahead a little bit, not bore you with tables of results of V-JEPA v2. One technique that we are working on now, and we have some results about this in the small cases, is really how how to prevent those systems from collapsing using regularized method. And one trick is to basically have an estimate of the content, the quantity of information coming out of the encoder. If you can maximize the information that comes out of the encoder, you will prevent the system from collapsing. And imagine that you pass a bunch of samples through the encoder. So each row in this matrix is a different sample, and each column is a different variable of the representation coming out of the encoder. You have two ways to kind of maximize the information coming out, contained in this matrix. One is you can make sure that all the rows of this matrix are different. So basically, every sample has a different representation. They don't all collapse to having the same representation. And so this corresponds to contrastive methods or sample contrastive methods. And then the alternative is to make sure that all the columns of this matrix are different. In other words, every variable in the representation carries a different information. Okay. One way to do this in the first case is to compute the gram matrix of this matrix, basically the product of this matrix by its transpose, and make sure that gram matrix is close to the identity so that all the samples are different or orthogonal. And this one is the converse. You compute the transpose of this matrix times itself, which is the covariance matrix, and try to make that covariance matrix close to identity. So this is a way of basically, kind of maximizing the information content in the representation, but it's approximate because we like to maximize information content, and we don't have any lower bound on information content. We only have upper bounds for very deep reasons. The fact that we can't kind of model all the possible dependencies between variables. All the estimate of information content that we have are upper bound, are overestimations. And so it's a bit of an issue there. But this technique that works by getting the covariance matrix close to the identity works pretty well. Let me skip ahead to the last slide, essentially. Okay, so I have a bunch of recommendations here. Essentially, abandon generative models in favor of those joint embedding predictive architectures that don't predict in the input space, but predict in representation space. Predicting in input space works only if you have discrete symbols, but in the real world, physical world, you have to learn representations. Use the energy-based framework to really understand how this works. Probabilistic modeling basically leads to intractability and is unnecessary. Abandon contrastive methods in favor of those regularized methods I was telling you about. And I wouldn't say abandon reinforcement learning, but at least minimize the use of reinforcement learning, because reinforcement learning is extremely inefficient, requires many trials. And so you have to use it as a last resort. So when I say all of this, these are all the pillars that are the most popular concepts in machine learning at the moment. Doesn't make me very popular. Particularly the first one. Basically, you have to walk around with bodyguards in Silicon Valley. I'm joking. Basically, if you're interested in sort of getting AI to the next level, to human level AI possibly, or maybe cat level, don't work on LLMs, work on V-JEPA. Thank you very much.